Okay, so as we have, you guys wanted to say hi to everybody, right? So 1, 2, 3. Yeah, people are saying hi to Richard and Bart. Hope you guys are having as much fun as we are. Because that's kind of hard to top double integrals all together, let me tell you. So we can evaluate double, integrals. Wow, we'll get that learning target all in there. Over type 1 and type 2 regions. What was type 1? Type 1, well, the procedure to find that, if you're integrating with respect to y first and then x, when you sketch the region, you're imagining vertical lines going through the region. And as you've got all these vertical lines, the lower y bound is the lower curve, the upper is going to be the upper bound in the integral. Choose x values to get all such vertical lines. For type 2, if you integrate with respect to x first, so maybe we've got something that looks more like so, and you can say, wow, what if you'd have horizontal lines with the same right-left boundaries always? Here you're integrating with respect to x first. Imagine horizontal lines cutting through. The lower x bound is the left curve. The upper x bound is the right curve. And you choose y values to get all such horizontal lines. Well, as we look at example 1, we're looking at a couple of problems today. Right now you might very well be thinking, didn't we learn all of this yesterday? You learned a lot, but here are 2 problems that have a little bit of a twist to them. It says, find the volume of the tetrahedron. How many sides do you think a tetrahedron has? 4, right? You've got 4 sides, right? So you got 4 sides to a tetrahedron, and they're saying bounded by planes. Well, wow, we've got x plus 2y plus z equals 2. X equals 2y, x equals 0, z equals 0. And, as we wrestle with this, you can begin to think, well, maybe I'll just start, trying to graph out what's happening in regard to just the xy plane. Yesterday, we repeatedly went there. Here's the problem. Yesterday, one of you guys asked for us to draw the picture of a plane that was intersected with, I believe another plane, and a plane that was over a rectangular region, if my memory serves. And we began to even talk about what that plane looked like. And, you might remember we talked about traces, and we also talked about intercepts. And both of those ideas are good and valid. So if I were to take a look at an x-intercept, for example, that's letting y and z both equal 0. Guess what we'd get? X would equal 2. If I were to look at a y-intercept, that means let every variable except y equal 0. You can see right here that the x and the z would disappear, leaving us with y equals 1. And then for a z-intercept, well, to find the z-intercept, we'll have x and y equaling 0. Guess what z would have to equal? Well, I hope you could see quickly. It would be a 2. Now, the reason why I'm bringing this up is just a quick review of what we were doing yesterday. And you don't have to make a spectacular picture here. You really don't. But look, I guess what I want to point out is here's a x-intercept of 2, here's a y-intercept over here at 1, and here's a z-intercept at 2, and we'd have this plane, and we're only catching a faint glimpse of this plane. Imagine that this little triangle here is just a little cutout of a full piece of paper, so to speak. It's as if we build this massive giant ramp going off on this, and that triangle happens to be a part of it. Well, that's part of your tetrahedron. You see, we have our tetrahedron bounded by that plane, and kids can correctly say, well, wow, I imagine that the ceiling of that plane, of the ceiling of that volume, the top of it would be the plane that we're talking about right here. And it is. But we also have x equals 2y, and we've got x equals 0, and we've got z equals 0, and you think, oh my gosh, wow, what's going on there? First of all, z equals 0 is in fact the xy axis, that we're used to looking at. But speaking of that, let's go back to this plane very quickly and take a look at the xy trace. The xy trace. By the way, sometimes kids will say, why are you even doing that? That's where z equals 0. It's x plus 2y equals 2. By the way, that xy trace is going to be this right here, isn't it? Right? It's that little piece right there. And kids will say, well, why in the world are you even focused on that? Answer, we are going to look closely at the xy plane, right? And that's what we have done time and time again. We're going to do that even right now. We can say, wow, let's just investigate that xy plane. Why am I bringing that up? The x plus 2y equals 2 directly comes into play here. You could say that's where that plane that we've just talked about cuts into the floor where z equals 0. You'd say, oh, okay. And then you'd say, well, x equals 0. Well, that's, this, flat, plane that you'd get right here. It would be the yz plane, so to speak. That's where x would equal 0. That would be this line right here at x equals 0 on the xy plane. And then you'd say, well, what about x equals 2y? Well, x equals 2y is really the line y equals x all over 2. And that, guys, is a line that comes out like so. So we've got y equals x all over 2. This is just in that very flat xy plane. And, hopefully you can see really what is happening here. We've got this other line of x plus 2y equals 2. And on that z equals 0 xy plane, we're getting those two lines right here to cross. Where do you think they're going to cross? And that's where, my goodness, you might wonder if you could find a happy answer right there. You might have to do some solving. You might very well have to, solve that out a little bit. Every once in a while, kids might say, I don't know. Dare I say, could it possibly be at y equals a half? That's solving by inspection. That's saying, look, I don't know if we're going to be lucky with this, but, my word, if it was, let's see, if y was equal to a half, look at that. If you had the line x equals 2y, when y would equal a half, what would x equal? A 1. And then you'd say, well, I don't know, in this other line right here, if x was equal to 1, if y was equal to a half, would that be true? Yes. Wow. Why do I bring that up? Sometimes, that's such a time saver, just being able to solve by inspection. So you could say, look, I have this floor, z equals 0, and I'm trying to find the volume above, and I am enclosed by, I hope you can see it now, I'm going to change the color, by this line, and by x equals 0 over here. I hope you can see that we're really dealing with this little triangular region, right? That's really on the floor where I'm going to be set up. So I'm going to go above that triangular region. And of course, I've got this slanting plane right here that we started, talking about. And, we're going to be finding that volume. Of course, we're making a tetrahedron. So at this point, do you think it's easier to have a type 1 or a type 2 kind of a region for what's in yellow? What do you think? Definitely, as you're thinking about it, you're saying, is it easier to have constant boundaries with these vertical lines or with horizontal? And the answer, I hope you can see, would be type 1, right? Kids will say, I want to do type 2. Well, your right boundary would be changing over time. So look, if you were to just draw on from here, you'd say, wow, I want to do a type 1 kind of a setup. Now with type 1, what's really happening is we're going to set up this double integral, and you can see what we're going to do in a type 1. We integrate with respect to y first, and then with x. And, what are we dealing with? What is the top of our function? It's going to be this plane. If I solve for z, if I were to slide over the x and the y, I'd get z is equal to 2 minus x minus 2y. That's really what we're going to have in here. So let's talk about those y boundaries. Look at the top here. That's the x plus 2y equals 2. Guys, if we were to solve for what y is equal to, we could definitely see that it's 2 minus x. Then we can divide by a 2. We'd get 1 minus x all over 2, right? So we'd get that. How about down below? What would our lower boundary be down here? That would be what? X all over 2. And then let's talk about our dx boundaries. What would that be? We're going to go from 0 all the way up to 1. You can see that's where all these vertical bars are being drawn in from 0 all the way up to a 1. Okay. We doing okay? All right. Well, then what? The rest of it gets to be pretty much a matter of just crunching these numbers out, right? Getting this all to work out. So we'll take a antiderivative with respect to y. We'd have, well, that's 2y minus xy. What's the antiderivative of a 2y? That's minus y squared. And of course, we're going to plug in our boundaries here and here. You get it. This is the mechanical part of it. Granted, when I say it's the mechanical part, it's also the ugly part. Let's be honest. You plug in your boundaries, you get 2 times 1 minus x all over 2 minus x times 1 minus x all over 2 minus, well, then we get 1 minus x over 2 squared. And, the rest of this whole process, guys, you're just going to be able to finish that up. And of course, like I was saying before, you're more than welcome to finish a problem like this, with an fn int. Of course, your 89 can do that too. As you work this through, you can say, I'm going to go from 0 all the way up to 1. And, then just typing this all in. Yeah. The lower bound? Oh my gosh, thank you so much. Wow. Yeah, thank you so much. Good thing you guys are here. Almost made a horrendous mistake trying to rush through this for the benefit of getting this video done. So sorry. My gosh, what was I just thinking? Thank goodness you guys are here. Even, at this point, do want to just tell you that, of course, even working this out by hand would just be tedious, right? It's going to be just tedious. And at this point, even typing this into the calculator is going to take a little bit of time. Let me just pause this for a moment. Pause things just to finish that off. You should just get very simply 3/10 or 0.3. We've got one more problem to do, and we'll have a separate video for that.